Hey guys, welcome back to Divide and Conquer Math, and this is the study series. So this is the third video in my study series that gives you practice problems to help you prepare for an exam on integration. So in this video, we're going to look at difficult integration problems. So if you've never used these videos before, I highly recommend that you actually consider starting with the first video. So that's kind of like the basic problems, just to make sure that you've got the foundation there. These problems are meant to be challenging. Now, the way that these videos work, you're going to want to download the problem set, which you can find in the description of this video below. And what we're going to do is, for the first hour, you will see me getting prepared to do the problem set. That's really a 1-hour timer to help motivate you to study. So if you feel like you struggle with getting started, consider just working alongside me, and I will time you for 1 hour and you know exactly what to work on. You can work on that problem set. Now, after you finish the problem set, or after the hour, whichever comes first, you can look at the problem set and find the answer key, and you can grade yourself. So anything that you didn't know how to do, you'll want to note that, or anything that you didn't get right that you want to see a worked out solution to. You can then look in the description of this video and you will find time markers for every single problem in that problem set, where I work out everything in its complete detail. So hopefully this will be kind of that one-stop shop to give you a really good variety of difficult problems to really get you prepared and kind of on your game for a calculus test. And you know what, why don't we just get into it? Let's start studying. Hey guys, if you're not done, hit pause now or you can start the study part of this video over again. So starting with the first problem, so I've got the, we need to integrate x over the square root of x plus 3. So this is going to be a problem that requires substitution where my u will be x plus 3 and my du will be just dx. Now you'll notice that there's a little bit of a problem here. So I've got this u part gets substituted right here, and then this du part will get substituted out with this dx, but we still have this leftover x. So in this type of problem, this doesn't mean that we did anything wrong. What we have to do is we actually have to manipulate here. So what I'm going to do is I'm going to notice that if u is equal to x plus 3, then my x is equal to u minus 3. So there's that relationship between those two things. And now I can make a substitution here with this part here, you see? So if I rewrite this integral now, this becomes u minus 3 on the top over, let's call this u to the 1/2 on bottom, and then this is du. So here's the substitution, and I've really changed the problem now, so I have to simplify all of this. So this is going to become now u to the 1/2 minus 3u to the negative 1/2, not 1/3, 1/2. And this I can integrate no problem, right? So now this will become u to the 3/2. I always like to add the 1 first, and then I multiply by the reciprocal of the exponent here. And then here, this will be 3 times, so let's see, this will be u to the positive 1/2, so this will be 3 times 2, and then all of that plus c. So my final answer then is 2/3 u to the 3/2 minus 6u to the 1/2 plus c. And now, okay, now my actual final answer will be 2/3 x plus 3 to the 3/2 minus 6 x plus 3 to the 1/2, and then don't forget the plus c. So for number 2, now I need to integrate x times the square root of 2 plus x. This is very similar to the first problem. So in this case, my u is going to be 2 plus x. My du will be dx. And now you'll notice that I've substituted out this part here. The dx is gone, but for this x now I'm going to have to manipulate my u. So if u equals 2 plus x, then x equals u minus 2. So I'll use that substitution to set this up. So now where I have that x, I'm going to replace it with u minus 2. Where I had the 2 plus x, I could rewrite this as u to the positive 1/2, and then this will just be du. So there's my setup. And now with how I have this set up, I actually need to distribute what I have here. So this will become u to the 3/2 minus 2u to the 1/2. And so now that's what I need to integrate. So to integrate this, this becomes u, so I always like to add 1 to the exponent first, and then I multiply by the reciprocal here. And then this will be 2 times, so let's see, u to the 3/2, and then again I multiply by the reciprocal here, and then plus c. So then my final answer will be 2/5, 2 plus x to the 5/2 minus 4/3, 2 plus x to the 3/2 plus c. And so that would be my final answer. Okay, so for number 3 here, so I've got x plus 3 squared times x minus 3 to the 7th. So for this one, this one's definitely going to be a little bit tricky, okay? So I don't want to multiply these out, first of all, okay? So I do want to use substitution, and what's kind of leading me towards what I want to substitute is the thing that is the, we'll say, like a nastier thing to have to actually try to multiply out. So this x minus 3 to the 7th, that to me is like a sign I should probably set that as my u. So my u will be x minus 3. And then my du, once again, will be dx. So now this means that my x is going to be equal to u plus 3. So I can make all these substitutions. Let me just be nice and clear with this. So my u here is going to go, that substitution will go there.
and then my du is just going to substitute out with my dx. And then for this last part here, this is what I'm going to substitute just right into the x. So that it's going to be this x plus 3. So where I have the x, I'm going to replace it with u plus 3, and then we'll kind of just work that out from there. So this becomes now u plus 3 squared times u to the 7th du. So I have to do some algebra now and kind of finish working this out. So sometimes we say in calculus the algebra is what will really get you. This could be one of those times. So you'll see now I've simplified this to u plus 6 squared times u to the 7th. I can't integrate this right now, okay? So I have to actually now multiply this whole guy out and then like simplify this all the way. So I'm going to bring this u to the 7th in the front. I'll go ahead and just multiply this stuff out. So here's what I'm left with. And so now if I distribute that u to the 7th, this becomes u to the 9th plus 12u to the 8th plus 36u to the 7th. So the whole idea here is you're just looking for something that you can actually integrate. I can't integrate this as it is. This I can't integrate either. This I can't integrate, like, because we've got all these squared terms, and you have to like work everything out until you get to a point where you can use some of the antiderivative formulas. And so when I get to this point, now I can use the antiderivative formulas. So that's really what you're looking for, and so sometimes it's a little bit of a journey to figure out how much work you have to do to get there. Okay, so now let's see, this will become 1/10 u to the 10th plus 12 times 1 over 9 u to the 9th plus 36 times 1 over 8 u to the 8th plus c. And so now I can replace all those u's with x's. So let me clear a little space here. Okay, so just to finish this out now, this becomes 1/10 u minus 3 to the 10th plus, let's see, this becomes 4/3 u minus 3 to the 9th plus, let's see, this becomes what? 9 over 2 u minus 3 to the 8th. Oops, sorry, I'm writing u's for all these. My bad. Those should be x's. X minus 3 plus c. And so there we go. Now, I think that this answer is really fine, but you'll notice that on the answer key I have a slightly different answer. And this is because sometimes I like to check my work against what like an online calculator might tell you. So I think this is okay, but I want to show you how do you actually simplify if you're expected to go farther. So what if this form is not good enough? So let's clear some space. So my new goal now is to make this into one singular fraction. So first of all, I've got these 3 fractions. These have a common denominator of 30, so I'm going to convert each one of these fractions to a fraction over 30. And then the other thing I want to point out here, so notice they do have kind of like a common term in that they each have this x minus 3. So what I'm going to do next is I'm actually going to factor out this x minus 3 to the 8th. I'm also going to factor that out, okay? So we got kind of a few things going on here. So maybe I don't want to do too much too fast here. So if I go in pieces, if I convert each of these fractions to just a fraction over 30, this 1/10, this will become 3 over 30. 4/3 will become 40 over 30. And 9/2, what'll that be? That will become 135 over 30. Okay, so let me factor out now 1 over 30, so I'm factoring out that fraction, and then I'm also going to factor out that x minus 3 to the 8th like I was talking about. So what does that leave me with for the rest of this problem? So you got to just take your time now. So I'm going to use a square bracket. So I factored the 1 over 30 out of this, so this leaves me with 3, and then I factored out x minus 3 to the 8th, so 10 minus 8 is 2. So this will leave me with this x minus 3 squared. Okay, you see how that works? Then, continuing on, so I factored the 1 out of 30 out of this, so that leaves me with the 40. And then just one factor of the x minus 3. And then for this final part, this is plus 135. And then all that plus the c still, okay? So now I have to simplify all of this stuff, okay? So kind of a long haul with this problem if we really want to simplify it. So I've got x minus 3 to the 8th over 30. And then, let's see, this becomes 3 times x squared minus 6x plus 9 plus 40x minus 120 plus 135, all of that plus c. So let me clear some more space. Okay, so now I've got x minus 3 to the 8th over 30 times 3x squared minus 18x plus 27 plus 40x, and then let me combine the minus 120 with the 35, so that becomes plus 15. Okay, so now if I try to finish this up, I get x minus 3 to the 8th times 3x squared plus 22x plus 42. All of this can go over 30 plus c. So it's a little bit more work. So there's a phrase we have in calculus that it's not the calculus that's going to hurt you, it's the algebra. Oops, and this should be a rounded bracket, sorry. And this is one of those problems where, like, if you are expected to simplify all the way down, this would be how you would do that, okay? Okay, so moving on to 4 here. So now I've got x over x squared plus 5 to the 5th. So this is another substitution problem. So this will be my u is x squared plus 5. My du will be 2x dx. And so this one is actually pretty straightforward, actually, because I don't have to like manipulate this x, so that's nice. So now if I make some manipulations here, I notice this is x, not 2x, so I do have to manipulate this to become 1/2 du equals x dx, and that's what I'm looking to substitute, x and dx. Okay, so now if I make these substitutions, I have 1/2 du over u to the 5th. Okay, so now this is really just going to be, so this will just be 1/2 u to the -5th du. So this will be 1/2 times, so I always like to figure out the exponent first. If I add 1 to this becomes -4, and then I multiply by the reciprocal, which would be -1/4, so this is what I would have. So my final answer now will be -1/8. Actually, I'll write this as a fraction. This will be -1 over x squared plus 5 to the 4th plus c. So this one really wasn't that difficult, but I did want to throw something in here just in case. Like, sometimes we get in this mode of like, oh, I have to make the problem super hard because everything should be really hard. This one was pretty straightforward, so just trying to make sure you're staying on your toes here as you're going through these. Okay, so for number 5 here, so now I have 4x to the 8th times the square root of x cubed minus 4. This one is definitely a tough problem. So, okay, the u in this case, let's see, I'm actually going to give myself a lot of space here. The u in this case will be x cubed minus 4. So you might have kind of that guess, but the problem with this particular problem is that when you take du, this is going to kind of mess with your head. So I get 3x squared dx, and you look back at the problem and say, oh, but I have 4x to the 8th. And then maybe you start to second guess yourself and say, oh, maybe my u has to be, you know, like x to the 8th or something. And then my du would be what? It would be 8x to the 7th. So This definitely doesn't work, dx. This definitely doesn't work because this x to the 7th, we have like no x to the 7th reference in here, right? So it's kind of better like when you're making a guess with your du, it's okay if the exponents come out a little bit smaller than your situation. But if I am left with an exponent that's a little bit bigger, like there's absolutely no way to substitute this out. This I might be able to work with if I make some manipulations, if that makes sense. So you got to be a little patient and creative now. So I'll get rid of all this. So here is now what we want to think about. If my u is x cubed minus 4, then x cubed is equal to u plus 4. Okay, so here's the question. How do I relate x to the 8th to my u's and my du's? Or maybe how do I relate my x to the 8th dx? We could think of it that way. Well, I could think of this as really being x to the 3rd times x to the 3rd times x squared dx. Do you see where I'm going with this? So I have then this x to the 3rd. I figured out this manipulation here. I've got an x squared here, so I might be able to manipulate this to make this work for me. So let's manipulate this to be 1/3 du equals x squared dx. And so now look what I've got. I've got these x cubes, those can both be replaced, and then I've got this x squared dx can be replaced here. So I have now figured out how to make kind of all these substitutions. So just to be clear now, my x to the x dx will be equal to u plus 4 times u plus 4 times 1/3 du, which I can rewrite this then as x to the 8th dx. This is u plus 4 squared. Let's actually bring that 1/3 in front, sorry. 1/3 u plus 4 squared du. So that was a lot of work. So sometimes when you're doing substitution, it does require like a certain level of creativity and patience. That's probably the hardest thing about these types of problems, and you want to develop that patience with these types of problems, because when you get further along in integration, like when you get to integration by parts, this gets even harder. So you really need to learn this patience right now, okay? All right, so let me clear some space. And now let's go through the fun times of making all these substitutions. So this becomes now 4 times, so this x to the 8th I'm now going to replace with this stuff here by all that work that we did earlier. 1/3 u plus 4 squared, and then this will be u to the 1/2, and then du. So there's everything all substituted in now. So you can see we still have quite a bit of work to do, right? Like we're nowhere near done. So now I'm going to have to multiply all of this out together and then distribute. So this is a longer problem. So what I'm going to do is I'm going to clear some space. And let's see, I'll bring the 4/3 out in front of the integral. And so then I'll bring this u to the 1/2 here. This is u squared plus 8u plus 16 du. So now I've got 4/3. And this is u to the 5/2 plus 8u to the 3/2 plus 16u to the 1/2 du. Okay, so now finally I have something I can actually integrate. This I can work with. Okay, so once again I'm going to clear some space. Okay, so now I've got 4/3. Make a big square bracket here. So this will become u. I always like to add 1 first, so this will become u to the 7/2, and then I multiply it by the reciprocal like so. And then this will be 8 times, let's see, u to the 5/2 times 2/5, and then 16 times, let's see, this will be u to the 3/2 times 2/3, all of this plus c. So now we can finish this out, and I'm going to go ahead and also multiply by this this 4/3 right in the front here. So let's see, I get 8 over 21. And then this becomes x cubed minus 4 to the 7 halves. And then let's see, this will be 4 times 8 times 2. So this is 64 over 15 x cubed minus 4 to the 5 halves. And then I've got 4 times 16 times 2, which is 128 over 9, and then this is x cubed minus 4 to the 3 halves, all of that plus c. Okay, so technically you could also simplify this even farther. I am just going to leave that here in this particular problem, but yeah, so there's the answer. If you looked this one up on a integration calculator, you might find that they simplify it way farther. And if you are looking for just some guidance on like how to do that, in problem number 3, I showed kind of that kind of crazier simplification, but I'm just going to leave that this answer as it is. Okay, so number 6, this is so we're integrating 1 over 1 plus e to the x. This is a tough one. This is actually one of those ones. This is one of those ones where you like really need to know the trick for this, and sometimes you might not know that this is a possibility. And don't get frustrated with that. So let me just show you the only way you can really approach this. So the first thing that you need to do is you need to multiply everything by e to the negative x. So this is, like I said, this is a trick. The reason why we have to use this trick is if you were to try to just do substitution as this is, you really can't. So just to show you, let's pretend for a second that I set my u as 1 plus e to the x, and so then my du would be e to the x dx. And so just looking at this, right, like there's no good way for me to substitute this out. And you can play around with this as much as you want, but you're not going to be able to get a good substitution. So what that tells me is I have to make a big change to how the problem is stated so that I can actually use substitution. So this is a really common trick for harder problems like this, but if you've never seen it before, then it can feel very difficult. So it's just one of those things where, you know, practice makes perfect. So let's go ahead and do this. So if I multiply all of this by e to the negative x, I'm going to get, so let's see, I'm going to get e to the negative x over, so 1 times e to the negative x is e to the negative x, and then e to the x times e to the negative x will give you e to the 0, which is just 1. So I've multiplied this whole fraction by the same thing. So every part of it by e to the negative x, and I've gotten this expression. So these are equivalent to one another, but with this I can actually do a substitution. So now if I set my u equal to e to the negative x plus 1, so what would my du be? Then my du, remember you got to use the chain rule here, this will be e to the negative x times negative 1 dx. And this is all good, right? So this I can manipulate into negative du equals e to the negative x dx, and now this part here, so which was right here, that can all be substituted out. So if I do my substitution, now I get negative du over u. No problem, right? That one we can definitely finish. This is going to be the negative natural log of the absolute value of u plus c. So my final answer is the negative natural log of u, e to the negative x plus 1 plus c. So that's definitely a tricky one. Okay, so for number 7, so now I've got a definite integral here going from 0 to pi over 4. This is 1 minus cosine of 2x times sine of 2x. So here's another case now where you're going to have to use substitution. And so in this case, my u will be 1 minus cosine 2x, and then my du will be 2 sine 2x dx. So I'm going to have to manipulate my du. So this will be 1/2 du equals sine 2x dx. So now I can make my substitutions if I wanted to. But since this is a definite integral, the fact that we have these limits of integration, this changes things a little bit. So there's more than one way that you can approach these. What I like to do is I like to also flip my limits of integration. So the way I do that then is I use this u and I say, okay, so starting with this, so if x equals 0, then if I plug that in to my u, well, this will be 1 minus cosine of just 0. So that'll be the x coordinate. So this will just end up being 1 minus really 1. So this whole thing will just equal 0. So no change in the value. And then if x equals pi over 4, then let's see. This will become cosine of, really when I simplify this, pi over 2, right? Because this is 2x, so 2 times pi over 4 will become pi over 2. So this will equal then, so the cosine of pi over 2 is 0, so this will just equal 1. So now I can just rewrite this whole integral going from 0 to 1. So notice how I swapped these out. And then the rest of this will be u times 1/2 du. And so that's something we can pretty easily solve. So let me clear some space. Now let's finish this. So this will become, let's see, this will be 1/2. So I bring the 1/2 out. So here's what I can integrate. So this becomes 1/2 times, so let's see, this will be u squared. So then I bring 1/2 out in front, and now I need to evaluate this from 0 to 1. So this will just be 1/4, and then really just 1 minus 0. So this will just ultimately equal 1/4. And so there's your final answer. We're done with that one. Okay, so for number 8, so this is another substitution problem. So for this one, I'm going to have my u, u, it's going to be 1 minus sine of x, and then my du will be negative cosine of x dx. And notice that in the actual problem, I've only got cosine x dx. I don't have the negative. So I'll just multiply both sides by -1 to get negative du equals cosine of x dx. Then, if x equals 0, we'll have the case that 1 minus sine of 0 is just going to equal 1. And if x equals pi over 3, then we have 1 minus sine of pi over 3. This will be 1 minus the square root of 3 over 2. So really the best that I can do with simplifying this would be to write this as just one singular fraction, which would be 2 minus the square root of 3 over 2. And now I can go ahead and make my substitutions like this. So this will become 4 over u negative du. So I want to kind of simplify all of this. So let me clear some space. Okay, so now if I were to rewrite this, let's bring the -4 out in front, and then I can just finish this up pretty easy. So this will be 1 over u du. So this equals -4 times the natural log of the absolute value of u, just that. And then I need to evaluate this from 1 to 2 minus the square root of 3 over 2. So this will be -4 times the natural log of 2 minus the square root of 3 over 2. Now notice I dropped the absolute value because I know that this is positive, so I don't need the absolute value. So it's this minus -4 times the natural log of 1. Now the natural log of 1 just equals 0. So the final answer here then will be -4 times the natural log of 2 minus the square root of 3 over 2. And I guess I can put parentheses around that if I want, but there's your solution. Okay, so for number 9, so I've got this definite integral of tangent x. So if you look at your list of antiderivative formulas, there is no antiderivative for just tangent of x. So this is actually a substitution problem in disguise. So what you have to do for this one is you have to rewrite it in its sine of x over cosine of x form, and then you can do the substitution. So in this case, so my u will be cosine of x, and then my du will be negative sine of x dx, which would make negative du equal to sine of x dx. And then I also want to switch up my my limits of integration. So if x is equal to pi over 4, then my u of cosine of pi over 4, so you have to think about your unit circle, what does that equal? This is the square root of 2 over 2. And then if x is equal to 3 pi over 4, then my u, which is going to be equal to cosine of 3 pi over 4, this is going to equal negative square root of 2 over 2. Okay. So now, if I make all these substitutions, so this becomes negative square root of 2 over 2, this becomes square root of 2 over 2, and then I have negative du over u. Okay, so a couple of things. Now you'll notice that with my limits of integration, so just with how this was evaluated, so now the most negative one is on top, so I can actually flip all of this and then get rid of this negative, so this would just become positive square root of 2 over 2 over negative square root of 2 over 2, and then this is 1 over u du. Okay, so that's one thing I just want to point out here. Now, the other thing I want to notice about this, so think about what happens. So if I have this function f of x equals 1 over x, so what happens if I plug in negative x? This becomes negative 1 over x. So this is equal to negative f of x, which means that this is an odd function. And so because this is an odd function then, and because we have this relationship here, we actually don't have to go any farther with this problem. And if you went farther with this problem, it would get a little tricky. But like, so because we have this symmetry and then we have the positive and the negative version of these limits of integration, I know right away just by looking at this, this is going to equal 0. But what if you didn't notice that? So let me continue on with the problem. So to finish this, what I would get is that this would be the natural log of the absolute value of u from negative square root of 2 over 2 to the square root of 2 over 2. Okay, so now this is going to be kind of interesting. What's going to happen with this? So let me clear some space. Let me clear out kind of all this stuff to the side. Okay, so now I've got the natural log. So I've got the natural log of the square root of 2 over 2 minus the natural log of the absolute value of the negative square root of 2 over 2. So when I take the absolute value of this, this will become positive. So then I just have the natural log of the square root of 2 over 2 minus the natural log of the square root of 2 over 2, and so that will also equal 0. So a couple different ways you can look at that. This is definitely the longer way to go, but if you notice that it was symmetric, then you would get this one done much quicker. Okay, so for number 10, so now I have the definite integral from 0 to the natural log of 3 of e to the x over 1 plus e to the 2x. So this is kind of another tricky problem. So I think a natural thing a person might think when they're working on this is that your u would be the whole denominator, but you can tell right away that this is not the right u, because when you take the derivative, this becomes 2e to the 2x dx, and what we really need our du to be is just this e to the x. So this does not work, okay? What does work, and this is kind of clever, would be to use just e to the x, and then my du would be e to the x dx. And you might be thinking like, oh, I don't know how to actually implement this. So let's clear a little space. Okay, so e to the 2x, this is really just e to the x times e to the x. So now if I replace those both with u's, this would just be u times u, so this would be u squared. So this 1 plus e to the 2x, I'm now going to write it as 1 plus u squared, okay? So we still have to work on the limits of integration, so let's also just deal with those real quick. So if x equals 0, then my u will equal e to the 0, which is just 1. And then if x equals the natural log of 3, then my u will equal e to the natural log of 3, so that's just going to equal 3, okay? So now I can go ahead and perform this substitution. So this becomes du, oops, let me fill in my limits of integration. This goes from 1 to 3, and then this is du over 1 plus u squared. And so that is going to be something that we can integrate. So this is going to be inverse tangent. Okay, so now to finish this, we just have to plug in our limits of integration here. So let's see, I guess I have just enough space to finish this. So this will be inverse tangent of 3 minus inverse tangent of 1, and that actually has a value. So inverse tangent of 3, I can't simplify that any farther, but the inverse tangent of 1 will be just pi over 4. And so this part right here, this is your solution. Okay, so for number 11, so for this one I have another definite integral. So this is going to be another case of substitution. So in this case, I'm going to use my u is equal to the natural log of x, and then my du will be 1 over x, and then I want to change my limits of integration. So if my x is equal to, if my x is equal to e to the third, then my u will be the natural log of e to the third, and so then just using log properties, so the natural log of e is just 1, and then you can just bring down that exponent, so this will just equal 3. And then if my x is e to the fifth, this will be u to the natural log of e to the fifth. So you've got that. Okay, so now I can actually go ahead and substitute this out, and just to be clear with this, because this one might mess with your head a little bit, so here's my u right here, and then this 1 over x, so this part and this, so there's my du. Oops, and sorry, I just realized when I wrote my du, I forgot the dx, my bad. Okay, so now if I go ahead and substitute, I'm going to go from 3 to 5 of 1 over u to the fourth du. So if I integrate this, this becomes u to the negative third, and then I can multiply that by negative 1/3, and so then I just have to plug this in from my limits of integration. So this will become negative 1 over 3 times 125 plus 1 over 3 times 27. So that's me plugging in my limits of integration. And so this, if I work this out, you can either do the work to get a fraction. So the fractional value of this, I'm going to just skip over this work, but the fractional value of this is 98 over 10,125. Or if you just used a calculator to get a decimal value, this comes out to 0.00969. Okay, so for number 12 here, so I've got another definite integral. So for this one, so once again I'm going to use a substitution here. So my u is going to be 4 plus the square root of x, and then my du will be 1/2 x to the negative 1/2 dx. And so you'll notice then that's exactly what this piece is here, right? So this 1 over square root of x, that would be this and the dx. So I just have to deal with, what do I do with this 1/2? So I'm just going to multiply both sides by 2. Get 2 du equals 1 over the square root of x dx. And now I can make a nice substitution. I also want to change my limits of integration. So if my x is equal to 1, then my u is going to be equal to 4 plus 1, which is going to equal 5. And if my x is equal to 9, then my u is going to equal 4 plus 3, which will equal 7. So now I can make my substitutions. So this will become 1 over u to the 5th, all of that times 2 du, and I have to plug in my limits of integration, so this goes from 5 to 7. Okay, so now I want to just rewrite this one more time, so I'm going to bring the 2 out in front, and this becomes u to the negative 5th du. So now if I work this out, this becomes 2 times, let's see, u to the negative 4th, so I always add 1 to the exponent, and then I multiply by the reciprocal over here. And I need to evaluate this from 5 to 7. So what I get here then is, this comes out to negative 1/2 times 7 to the 4th plus 1/2 times 5 to the 4th. So there's kind of all the math that goes into that. And I'll just tell you, so if you're plugging this in, so this comes out to the decimal value, 0.00059, and it actually goes on 175. So there's the decimal value that I got. Okay, so for number 13, this is also a very tricky problem. This one is probably one of the hardest ones in this set. So this is another problem where there's a trick to this, and you have to just be patient and kind of be willing to play around with this to figure it out. And once you see the trick and you know that it's something that you can do, these types of problems, they become more predictable, but you have to practice them a lot. So don't get frustrated if you tried this and you realize like, oh, I didn't get it immediately. That's not necessarily like a sign that you're not good at this. This is a hard problem. So you might have noticed, if, as you tried to do substitution, like maybe you tried to substitute out the denominator, and then it didn't make sense because you don't have like an x to the 12th on top here. And then if you tried to set your u equal to maybe the top, it still doesn't make sense because then you have no way to get to the denominator. So what you might have done first is just try to go through all these different possibilities, and perhaps you even went a little bit farther and tried to break up this fraction. So the actual way to approach this problem is you need to simplify part of this radical, and you have to do it strategically for the denominator. So I'm just going to show you how to actually approach this. And if you're just watching this solution and you haven't tried this on your own, I would highly recommend that you pause this video and try this a couple different ways before you watch this solution, because this is a tough one, but it won't make sense unless you've spent a little time kind of like banging your head against the wall, as we say, like trying to figure it out. The solution will feel a lot more meaningful if you've spent that time figuring out why is this hard. Okay, so let me clear some space. Okay, so I'm going to break this down. I'm going to rewrite this as, so x to the 5th minus 2x squared. But then this x to the 13th, I'm going to break this up as x to the 8th and x to the 5th. So all I've done is kind of split up this denominator. But what that's going to allow me to do is I can actually go ahead and evaluate this part right here. So this is the square root. This is the only part of this square root that I want to evaluate, okay? So in doing that, what is the square root of x to the 8th? This would become 1 over x to the 4th. So that's just me taking the square root of this part here. Everything else that you see, I'm going to leave under the radical. But watch how this strategic choice of how I simplified this, how this is going to change the problem. So now what you'll notice is that I can simplify the inside of this radical, and I'll actually lose part of like the fractional components of this expression. So let's clear a little space. And now I've still got this as 1 over x to the 4th, but now this part becomes x to the 5th over x to the 5th minus 2x squared over x to the 5th. And this is where this is going to be very clever and kind of a brilliant workaround, if you will. So this becomes 1 over x to the 4th. Now this simplifies to 1 minus 2 over x cubed dx. Okay, so here's where we try substitution again now. Now what I'm going to do is I'm going to set my u equal to 1 minus 2 over x cubed. And so then what's my du in this case? Well, then my du would be negative 2 times negative 3 x to the negative 4th dx. So this would simplify then to my du would be 6x to the negative 4th dx. And look at this now. This is literally equivalent to what we have left over in the problem. So it's a very strategic way that you have to break down this particular fraction for this to work. So now I need to manipulate this one more step. So I don't have a 6 anywhere in this problem, so I just need to divide out the 6. So I have 1/6 equals, and I'll write this in its fractional form, 1 over x to the 4th dx. Oops, and I lost the du. Let's see, 1/6 du. Okay, so now I can substitute everything out. So just to kind of review this, so my u is right here, and then this du part is going to be substituted out here. So hopefully that's all clear now. So let me clear some space. Okay, so now let's go ahead and substitute. So this becomes the square root of u times 1/6 du. Okay, and so now let's bring the 1/6 out, and I'll rewrite this as u to the 1/2 du. So if I evaluate this, this becomes 1/6 times, so I always like to first figure out the exponent. So 1/2 plus 1 will give me 3/2, and then I multiply by the reciprocal. So this will equal, plus c. So ultimately this will equal, let's see, 1/9. 1 minus 2 over x cubed to the 3/2 plus c. And so that would actually be the solution. So that was definitely a very tricky problem. Okay, so for number 14, so this is a definite integral. This is, I think this might be the hardest one on here. It's a toss-up between this one and the previous problem. So there are so many different things that you could probably try with this that will not work. It's something very specific. It's another case where you have to be very creative in a very specific way. If you don't know why this problem is hard, then I want you to pause the video and try this at least 3 different ways. At least 3 different ways to see if you get it. And if you get it, that would be awesome. I'd be so proud of you. But if you don't, it's okay. I'm just going to show you the right way to do this. Okay, so first and foremost, this is a problem that's going to require some manipulation, and it's going to require a manipulation that I don't think most people would think of. So what we want to do is we want to manipulate tangent squared x, and we want to rewrite it as secant squared x minus 1. So tangent squared x plus 1 equals secant squared x. We're using one of the Pythagorean identities for this, so we're going to rewrite it like this. And so in rewriting this problem, so remember, secant x is equal to 1 over cosine of x. So if I were to multiply this out now, I change the problem. So this becomes 0 still to pi over 3. So this will become, this would be then just secant x minus cosine x dx. So make sure you agree with that. So secant squared x, so this is really 1 over cosine squared x. So if I multiply that by cosine, one of those cosines will drop out. So then I'm just left with secant x, okay? So here's the deal. I'm gonna split this up into two separate integrals. Like I said, this is kind of a tough one. So I need to deal with secant x dx, and then I have this other one, just cosine x. Okay, so look at these two integrals. So which one can you go ahead and just evaluate? We can evaluate this one, no problem, okay? So what I'm going to do is I'm going to pivot here, and I'm going to take a moment to just focus on the first part of this integral. So we're actually going to start a new page here to talk about this. So what I want to do is I just want to focus on how do we evaluate this. Because you can't even use substitution just by looking at this, and we don't have a nice formula to finish this. We have an antiderivative formula for cosine x, but not for secant x. So the only way you can actually deal with this is by making a pretty crazy multiplication. And that's going to be secant x plus tangent x. So if I multiply secant x plus tangent x over secant x plus tangent x, this is equivalent to just 1, so I don't change the value of this problem technically. But notice what happens when I multiply secant x times the top. And then you'll see how to hopefully finish this maybe. So the top will be secant squared x plus secant x tangent x over secant x plus tangent x dx. Now, like I said, this is kind of a journey. It's kind of a crazy problem. So now we can use substitution with this. So what's the derivative of tangent x? It's secant squared. What's the derivative of secant x? It's secant tangent x. So now we have a substitution problem where my u is going to be equal to secant x plus tangent x, and my du will be equal to secant x tangent x plus secant squared x dx. So the substitution will work quite nicely. And then if my x is equal to 0, then my u is going to be equal to secant of 0 plus tangent of 0, so that equals 1. And then if x is equal to pi over 3, then I need secant of pi over 3 plus tangent of pi over 3, and that equals, let's see, so secant pi over 3, that's going to equal just 2. And then tangent of pi over 3, so remember you're taking sine over cosine, so that'll just be, let's see, just the square root of 3. I think that's it. Let me double check my math. Yeah, that's right. Okay, so now I can make these substitutions into this integral here. And I'm like totally out of space, so let me clear some space. Okay, so now my integral is going to go from 1 to 2 plus the square root of 3. And then let's see, this becomes just du over u. Okay, so then this will equal the natural log of the absolute value of u. So I just need to plug in this. So at the end of the day, this becomes the natural log of 2 plus the square root of 3 minus the natural log of 1, and the natural log of 1 just equals 0, so that just cancels out entirely. So, bring this up, the answer here is just that part right there, okay? So now, this part right here, we just did all the work for that and determined that this was this, let's see, sorry. I just switched, like I had Microsoft had this update and now PowerPoint has stopped working in the way that I needed it to, so I had to just download a different version of PowerPoint. So if everything looks a little different, it's because like I just had this version swap that has taken me a couple days to figure out. So sorry for some of the clunkiness in this video. Okay, so I've figured this part out, so now I just have to finish this part here. So you know, why don't we just go to another screen and finish this other part of the integral. So I will now work out this part right here. So okay, so in evaluating this is easy peasy as far as integrals go. It's just sine of x. So I just need to evaluate that from 0 to pi over 3. So I just take sine of pi over 3 minus sine of 0. So this equals square root of 3 over 2 minus 0. And so here is, let's see, maybe I'll just do it in green again. So there's really my answer. So going back to this problem, so this will be minus square root of 3 over 2. And so now, now I finally have the answer. So that would be the solution to this one. So that was a tough one. Okay, so for the next few problems, we're just going to find the derivatives. So these are using the first part of the fundamental theorem of calculus. So these might look more challenging, but you're still just going to use really the fundamental theorem of calculus when you need to. So notice I start with like x squared. So taking the derivative of this, I literally just take the derivative of x squared. So this will be 2x, and then I use the fundamental theorem of calculus to finish this part here. So what I'm going to do is I'm going to plug this in, since this is square root of x and not just x, then I'm also going to have to use the chain rule. So the way this is going to work, so this will be 4 over the square root of 2 minus the square root of x. So I plug this part into the problem, and then I take the derivative of the square root of x. So this will be times 1/2 over the square root of x. So there's kind of all the pieces that go into this. So my final answer in this case then will be 2x minus 2 over, let's see, we have a couple different ways we can do this, I guess. So we could say square root of x times 2 minus the square root of x. I guess we could do it like that. And then if you wanted to take this a step farther, you could write this as 2x minus 2 over the square root of 2x minus x times the square root of x. So that would be another way you could write that. Okay, so for number 16 here, so once again we want to take the derivative, and the thing I want to point out here, this is going to require the product rule. Here's my first function, and this is my second function, okay? So you have to use the product rule with this. So, product rule, first I take the derivative of just x, which is just 1, right? And then I can just leave the second function alone, like so. And then I add to that and I leave just the x alone, and now I have to take the derivative of this. So to do that, I use the fundamental theorem of calculus, the first part. So I'll just draw a little star here. So this will be cosine of x cubed, all of that to the 4th. Now, since this is x cubed and not x, I have to use the chain rule. So now I have to multiply this by the derivative of this guy. So the derivative of x cubed is 3x squared. And so my final answer then is going to be a little big, but so I've got this definite integral plus 3x cubed cosine of x to the 12th. And so there is the final answer for that one. Okay, so for this last one, so I need to find the derivative. So with the fundamental theorem of calculus, normally we would have the x term up here. So I can manipulate this expression. I can just flip my limits of integration like so. And then I can go ahead and just take the derivative. So what I'm going to do is I'm going to plug this 3 to the x in for where there's the t. So my y prime will equal negative square root of 3 to the x. But now I have to multiply by the derivative of 3 to the x, which will be 1 over, or no, sorry, it'll be 3 to the x times the natural log of 3. And yep, so that's it. So then my final answer, if I just want to make this look nicer, this will be negative 3 to the x times the natural log of 3 times the square root of 3 to the x. And so that would be it for that one. Okay guys, so that wraps it up for this set of very difficult problems. Some of these were pretty darn tough. So I think this is a really great video to watch just to really kind of throw you off your game as you prepare for an exam. Super curious to know what you guys think of this. Feel free to leave a like or a comment. And otherwise, I'll catch you guys next time. Thanks for watching.